Okay, welcome back. So from last time on Friday, we were talking about this directional derivative, and we kind of rewrote it in a way such that we could write it as in terms of the partial derivative with respect to x and the partial derivative with respect to y. And we kind of introduced this concept of the gradient, which was a vector of the partial derivatives corresponding to that variable. So the first element was partial x, the next one was partial y, and so on. We were able to write the directional derivative in the direction of a unit vector u of a function as the gradient of that function dotted with the u vector. And we wrote that for any general Rn. So no matter what dimensionality we're in, we can write this directional derivative in terms of this dot product with the gradient. Okay, so let's start off with an example. We're going to find the derivative of this function f that's equal to x cubed minus x y squared minus z. We're finding this at the point 1, 1, 0. And we're going in the direction 2/7, negative 3/7, and 6/7, which is a unit vector. Okay, so we don't have to check if it's a unit vector. There it is. So to get started here, we need to find each derivative. So we need to find fx at the point 1, 1, 0. So we go ahead and take the partial derivative with respect to x of our function. So we get a 3x squared minus y squared. And we're evaluating this at 1, 1, 0. So we get the value of 2. So next, we're finding f partial y at this point. So we go ahead and take our partial y derivative. We'll just get a negative 2x times y at the point 1, 1, 0. This will just give us a value of negative 2. So then the partial z derivative at this point will just be negative 1. And we're evaluating at this point, but it's a constant, so we'll just get negative 1. So that means that our directional derivative of f at the point 1, 1, 0 is the gradient of f at this point 1, 1, 0 dotted with our u vector. Our gradient at this point is fx at that point, which we found to be 2, fy at that point, which was -2, and then fz at that point, which was -1. And we're dotting this with the u vector, which was given to us as 2/7, -3/7, and 6/7. So we can dot this out. This is 4/7 plus 6/7 minus 6/7. So we should just get 4/7. Okay, so now after that little warm up, let's talk about our next topic with this directional derivative, which is maximizing the directional derivative. So imagine you're at a certain point and you want to find the largest slope in a particular direction. What is that direction? Can we find it? Is there like a nice way of putting that? So in order to find the direction where the directional derivative of f is maximized, we're going to first note that the directional derivative which we wrote as the gradient of f dotted with u, we can use the dot product rule to say that this is the magnitude of our gradient vector times the magnitude of our direction vector times cosine of theta, where theta is the angle between those. Now, u is a unit vector, so we can get rid of it. It's just 1. So we can just write this as the magnitude of the gradient times cosine of theta, where theta is still the angle between the direction and the gradient vector. The max of our directional derivative then is the magnitude of the gradient, because the largest this can be is 1. So the largest value that our directional derivative can take is the magnitude of the gradient. And of course, this occurs when theta is equal to 0. That means when the direction that we're traveling in is the same as our gradient. So if we head in the direction of the gradient vector, we're going in the direction of steepest ascent. So we're going in the direction that has the largest slope. Now, vice versa, Imagine that you wanted to go in the direction that has the most negative slope, right? If you wanted to minimize the derivative where it's the largest negative number, you would want cosine to be -1, meaning that the minimum value of our directional derivative is then the negative of the magnitude of the gradient. It also means that the direction to achieve that minimum is when theta is equal to pi, or in the exact opposite direction as the gradient. So let's do an example. We're going to find the direction that maximizes our directional derivative at the location 2, 0 when our function is equal to x e to the y. Okay, so there's not much to this. That we know that the direction that maximizes the directional derivative is the direction of the gradient vector. So let's find that gradient first. We know that the gradient vector is the partial derivatives with respect to x and y. So we take our partial derivative with respect to x first. We just get an e to the y. And then we go ahead and take it with respect to y. We get an x e to the y. So then the gradient of f at the point 2, 0 is, we plug in 0 for y. So here we get just 1. And then we get, again, 1 from here, and then times a 2. So we get 1, 2. So this is the direction that maximizes the directional derivative at this location. We go in the direction of the gradient. We could also ask ourselves, what is that maximum? And for that, we would just need to calculate the magnitude of the gradient. So the max is then the magnitude of the gradient at 2, 0, which would be the magnitude of 1, 2, or √5. In the direction 1, 2. Now notice that we didn't have to write that as a unit vector because it doesn't ask for this unit vector here. If we were to take the directional derivative, we would need u to be a unit vector. But for the direction, we can just use 1, 2. This is perfectly fine. But in the definition, when we're actually calculating, the gradient of f dot with a u vector, we need to ensure that that u vector is a unit vector. Okay, so now we've got a big block of text coming up. We're going to talk about tangent planes to level surfaces. So bear with me. We're gonna write down some stuff and then we'll talk about it. We'll kind of talk about it along the way too. So we're gonna consider some surface that we'll call capital S in R3. So notice here that I don't say that it's a function, it's just some surface. So it doesn't even have to be a function. It could be like a sphere or like an ellipsoid, right? Just some surface in R3. And what we're doing is we're rearranging this we're going to rearrange the equation into f of x, y, z is equal to some constant. So regardless of what the defining equation is for the surface S, doesn't need to be a function. What we can do is we can rearrange it, guaranteed to write it as a function in a higher dimension. So we're going to R4 and we're writing it as a function in R4, and it's going to be equal to some K. So notice that means, I know you can't visualize what it means to be in 4 dimensions, but this is some function in R4 that is now equal to some constant value, and that's a level surface. So we've taken our surface in R3 and we're bumping it up into R4, and it's a level surface in R4. So this is a level surface in R4. If we let P at x naught, y naught, z naught be a point on S, then there is a curve that we'll call C that passes through our point P, but it also lies on S. So right now we're still setting up. So imagine this surface in R3. You don't have to think about R4 currently. So if we're still in R3, you've got some point there on this surface. There has to be a curve that is on the surface S, but also passes through the point P, right? And that's just kind of like how we've talked about doing limits, right? We're on this surface and we're going in certain directions. We're still on the surface and we're trying to get to a point P. So now we're continuing. So C can be written by a continuous vector function R of t is equal to some function for its x component, some function for its y component, and some function for its z component. So all we're doing is just parameterizing that curve C. Where the vector R naught is equal to our vector R at some time t naught. And this points to our point P. Since the path C lies on our surface S, any point x of t, y of t, z of t satisfies that if we plug in x of t, y of t, and z of t into our R4 function, this capital F, it's still on the level curve. Okay, all right. So what are we doing here? So what we did was we created this function in R4 that is a level surface, right? And it's based off of the surface S in R3, okay? So that means any point in S can be inputted into our function F and get us K. So now we're back to R3. We have a point on our surface, and there's a line, or sorry, a curve that's still on S that goes through our point P. Of course, that curve C can be parameterized. We can write it as a function of x, y, and z that are each functions of our parameter t. Because C is on S, it still needs to satisfy the equation in R4 for our level surface. So our inputting our parameterization into x, y, and z should still give us this level curve. Okay, but notice now that this is a function of x, y, and z that I have that each rely on this parameter t. So what I can do is talk about the derivative. So then, if we want to find df dt, this is partial f, partial x, dx dt, plus partial f, partial y, dy dt, plus partial f, partial z, dz dt, right? But I also have to do the derivative on the other side. I do the time derivative of this k value, and I get that it's just 0. Okay, so what does this relationship mean? It looks like df dt is equal to 0 and R4. Well, let's look at this segment right here. We can rewrite this. This is the gradient of our f function. Notice here. This is partial f, partial f, partial f, partial y, partial f, partial z. And then it's what we're going to say is this is dotted with dx dt, dy dt, dz dt. But if x, y, z is r, then x prime, y prime, z prime, this is equal to r prime of t. And we still have that this is equal to 0, this dot product. So now that we have the gradient of this capital F dotted with this derivative function, and we know that this is equal to 0, in particular, when t is equal to t naught, now remember at t naught, we're pointing to the point P. At this point P, we have that the gradient of f at x naught, y naught, z naught, dotted with r prime at t naught is equal to 0, right? It's always going to be equal to 0, but specifically we can look at this point. This means the gradient vector at P is perpendicular to the tangent vector to any curve that we chose C, because we chose C arbitrary, as long as it was on S and included the point P, on S, that passes through P. So this gradient vector is perpendicular to this r prime, but r prime was this parameterization, right, along a curve that was arbitrary, so long as it passed through P and was on S. But we could have chosen a number of different paths that satisfied that. But regardless of what path we chose, this gradient vector is always going to be perpendicular with it. So if the gradient vector at x naught, y naught, z naught does not equal 0, then the tangent plane to the level surface at P is the derivative with respect to x at x naught, y naught, z naught times x minus x naught plus the y derivative at x naught, y naught, and z naught, y minus y naught, plus fz at x naught, y naught, z naught, times z minus z naught is equal to 0. So this is a way for us to figure out what the tangent plane of a surface is rather than just a function. So I know we went through a lot, but remember when we were finding the tangent plane of a surface that was generated by z is equal to a function of x and y, right? So that's a function. What if I wanted to find the tangent plane to a sphere? Rather than divide up that sphere into the top half and the lower half and then going from there, what I could do is go through this whole process, right? And now this is the inclusive definition of this tangent plane. And the way that we got there was bumping it up to a higher dimension. So imagine that you had, x squared plus y squared plus z squared is equal to 1. You just had a unit sphere. Well, that is already this definition of this capital F, right? This x squared plus y squared plus z squared is equal to some constant. So all we need to do is just take those derivatives and then set up in this expression here, and this will be our tangent plane to the sphere at that point, x naught, y naught, z naught. Okay, so going from here, we have that another definition, the normal line to S at P is given by the direction of the gradient of our capital F at x naught, y naught, z naught. Because recall, it's always orthogonal to any curve that's on S that passes through P. So that means that it is pointing directly orthogonal to the surface itself. So at that point, x naught, y naught, z naught, we can find this normal line now, right? Because you can imagine a normal to a plane is this constant thing. But the normal to a surface is going to be constantly changing depending on what that surface is like. And this is a way to find that. So the symmetric equations of the line, rather than just the direction itself, are x minus x naught over the x derivative at our point is equal to y minus y naught, our y derivative at that point, and z minus z naught over the derivative with respect to z at our point, x naught, y naught, z naught. Okay, so let's do an example. We're going to find the tangent plane and the normal line to the surface x squared plus y squared is equal to 9 minus z. At the point 1, 2, 4. Okay, so I want to start off by saying this can be rewritten as a z equals f, right? Pretty easily. So we could find the tangent plane the old-fashioned way, right? But let's get some practice doing it for a general surface, doing what we've discussed just before, right? So kind of disregard that we can actually solve for z and then make this a function of just x and y and then find the tangent plane that way. Let's use this formulation that we did for any generic surface. So the first thing we need to do is define our capital F. And capital F is a function of x, y, and z that's equal to some constant. So I have to manipulate this. So I can move the z over, and then I have the constant 9 left over here. So I can say x squared plus y squared plus z is equal to 9. So this here will be my f function. The next thing we do is we find the gradient of our capital F function at our point, P naught. So the gradient of f is equal to, so we go ahead and take our derivatives. We get an x derivative that gives us a 2x. Our y derivative is just a 2y. And our z derivative is just 1. So the gradient of our capital F at P naught, when P naught is 1, 2, 4, this just gives us the vector 2, 4, 1. The plane is then, so all we just need to do is just plug and chug here. We have fx is 2 at that point, so we get 2 at x minus 1, because this is x naught, plus 4 times this y minus 2, plus 1 times z minus 4 is equal to 0. So we can go ahead and FOIL these out, and we can get a 2x plus 4y plus z is equal to 14. And that's our plane, right? I know the kind of lead up to this was kind of maybe a little bit brutal, but at the end of the day, the result is very nice and clean, right? We just find this capital F function, we find the gradient, and those are the coefficients in front of our x, y, and z terms for our tangent plane. Okay. you just disregard the 9 from the beginning. Then I need f equal to some constant. So 9 would be perfectly fine to leave over here. You could have subtracted 9 and have this equal to 0, but notice that all the derivatives will still be the same. That's why we need just some constant. Doesn't matter. So it doesn't need necessarily be equal to 0, it just needs to be equal to some constant. Okay, so now we're still not done. We still need to find the normal line. So we know that the normal line is in the direction of the gradient at that point. We could write it in terms of the symmetric equations, but let's write it in terms of the parametric equations here so we get just kind of another idea of what's happening. So this is the vector that's pointing to P, and the direction we're going needs to be perpendicular with the tangent plane at that point, which is in fact the gradient of f. So this is 1, 2, 4 plus 2, 4, 1 times t, or 1 plus 2t, 2 plus 4t, and 4 plus t. Okay. So we've already kind of seen in this section alone that we've introduced this gradient and it's showing up. It's going to be really important. It helped us kind of figure out what the normal direction to a surface was going to be. And that concludes our section for 11.6. Why don't we take our 5-minute break here, and then we'll continue with 11.7 when we come back. Let's start section 11.7. We'll talk about maximum and minimum values. So a function of two variables has a local maximum at AB if f of xy is less than f at AB, or less than or equal to AB, where or when xy is near AB. This just says in a very small neighborhood around the point AB, f has the largest value in that small neighborhood. And if you make that neighborhood smaller and smaller and smaller, it still remains true. The number f at AB is called a local maximum value. If f xy is greater than or equal to f at AB, where we have some neighborhood around AB, then the point AB is a local minimum. With a local minimum value f at AB. Okay, so that seems kind of self-explanatory when you're thinking about local max and mins. Everything in a small neighborhood around it is either smaller or equal to it in terms of a local maximum, or greater than or equal to it in terms of a local minimum. So let's consider some function of two variables, x and y. And we're going to let g of x be the function along the y equals b trace. If f has a local max or a min at the point AB, then the function g of x has a local max or min at x is equal to a. And we know from Calc 1 that the derivative of g at that point a is equal to 0. So notice this means that the partial x derivative at AB is equal to 0. So we can repeat this logic along the x is equal to a trace as well. So maybe we have a function h of y that's equal to f of ay. Now, if AB is a max or a min, then we know that H has a max or a min at B, which the same logic applies, that means we also have that the derivative of H at B is equal to 0, thus implying that the y derivative of f at AB is equal to 0. So that brings us to our theorem here. If f has a local max or a min at AB and first order partial derivatives of f exist at AB, then we have that both the x and y derivatives are equal to 0. So notice that this doesn't say if and only if, or meaning that it doesn't go both ways. If f has a local max or a min at AB, then its derivatives are certainly 0 there, right? But the derivatives being 0 there does not imply that it is a local max or a min. So we have to kind of continue this idea here. If we have that these derivatives at the point are equal to 0, and notice that they both have to be equal to 0, not just one, then what we do is we say that the point AB is a critical point. So note that not every critical point is a min or a max, right? We're just saying that anywhere that both of the derivatives, x and y, are equal to 0, that can be classified as a critical point. We also consider points where fx and fy do not exist, critical points. So anywhere where the derivatives don't exist, we also kind of classify those as critical points because we can't rule out that those are in fact mins and maxes as well. All right, so let's do an example. we're going to find the critical points of the function x squared plus y squared. Well, the first thing to do is look at each of their partial derivatives. So we have that the x derivative gives us 2x, and we have that the y derivative gives us 2y. Now, for a critical point, it's not that one of them is equal to 0. It's that both of them are 0. So here I get that x needs to be 0, and here I get that y needs to be 0. So the only point that ensures that fx and fy are both 0 is the origin. So the only way is to have the origin. So the origin is the only critical point that we have for this function. Okay, so if you remember back from Calc 1, where maybe we're asked to find these critical points along this function. So you set the derivative equal to 0. You found where that happened. Those are your critical points. But then you needed to figure out if they were local min, maxes, or otherwise, right? And one way to do that was the second derivative test. So the second derivative test does exist in this higher dimension, but we have to be a little bit more cautious with it. It's a little bit more elaborate because now we have directions going from all around rather than just from the left and right. So suppose the second partial derivatives of f are continuous. On a disk with center AB. And suppose that the first derivatives with respect to x and y at that point AB are equal to 0. What we do is we're going to define what's called this like discriminant It's a function of x and y that we'll input a and b into, and it is fxx at AB times fyy at AB minus fxy at AB squared. Really, where this is coming from is a determinant. because you can think of all of the second derivatives being a quantity that is characteristic of concavity, right? And to get an idea of the concavity, because you have concavity in every direction, you have to kind of have a measure for the total concavity, or some kind of like way of systematically kind of characterizing what that means in all these directions. One way to do that is through this determinant. We're never really going to calculate out this determinant. We're just going to use this line right here. And you can kind of notice here, because we specifically said that the second derivatives were continuous around AB, that means that the order of these diagonal derivatives here, fxy and fyx, can be rearranged. So we can say that they're the same thing, and then that's why we have this squared here. Okay, so now that we've defined this d function, let's go through the options. So we can have that f has a local max at AB if we have that fxx is negative and d is positive. Okay, so let's kind of dive in why this makes sense, and this is how your book lists it, and I'll talk about that you can also have fyy here. They just arbitrarily pick fxx, but you can also check fyy. So fxx and fyy are your definitions of Calc 1 concavity in the x direction and this y direction, right? So long as this is a local max, it definitely makes sense that the concavity in the x direction or the y direction, or in fact any direction, is negative. So that's why you can test either fxx or fyy, right? And if they're both negative, that means that their product ends up being a positive quantity. This mixed term is kind of like how the derivative changes in the orthogonal direction. We won't kind of dive into the specifics and like how this was derived. That'd be too long. If you want, you can look it up. It's not in your book. You could look it up online, or we can talk about it at some other point. But let's just go through the options here. So you can test fyy instead of fxx. Okay. Another option is that f has a local min at AB if I have that fxx is positive and d is positive. So same thing here. You can also test fyy instead of fxx, because the concavity in that corresponding direction should be positive. This is a local min. So C, f has a saddle point at AB if D is negative. So a saddle point more or less kind of corresponds to, it has a max in one direction, but it is a min in another direction. And we can kind of think about that in terms of what's happening with our discriminant here. If it's a max in one direction, and a min in the other, I'll have a negative and a positive in this product, right? So I'll overall get a negative quantity. This certainly, because it's squared here, will always be a subtraction of a positive quantity. So I'll get a negative number. So that certainly means that I had a max and a min in different directions. And then we finally have our fourth option here. The test is inconclusive at the point AB if D is equal to 0. So if D is equal to 0, you're in trouble. You can ask me, oh, what do I need to do if I can't use the second derivative test at the point AB? There's no clean answer. For whatever surface that you're working on or whatever the function is, it's going to be a totally different thing. There's no cut and dry, oh, I need to take this approach or I need to take this approach. You have to be clever if this is inconclusive. So cross your fingers, hope that it's not. Okay, so let's do an example. We're going to find the extreme values of the function y squared minus x squared. So with any problem like this, we're going to start by trying to find the critical points. So we look at each of the first derivatives with respect to x and y. For x, we get negative 2x. And for y, we get 2y. Again, just like the previous example, the only spot where fx and fy are both equal to 0 is when we're at the origin. So we have the point 0, 0. So our discriminant at 0, 0 is fxx at 0, 0 times fyy at 0, 0 minus f of xy at 0, 0. And this is squared. Okay, so we take our second derivative, we plug in 0, 0. Well, the second derivative of f, so with respect to x, this is just going to give us a negative 2. We don't even have to plug in 0, 0, it's just this constant. And then we take the second derivative with respect to y, we get 2. And now we're subtracting fxy or fyx, because these are going to be continuous functions, doesn't matter which order we do it in. It's going to end up just being 0. So this is going to give us negative 4. And we can look at our list from above and say, since D is negative, we know the origin is a saddle. point. In fact, we can even think about this a little bit more, and we can say that because of the concavity, we know that this is negative in the x direction and positive in the y direction. We know that this is a max in the x direction. And a min in the y direction. Okay, so why don't we do another example? So this time we're going to find local extreme values of the function of x and y. So x times y minus x squared minus y squared minus 2x minus 2y plus 4. Okay, so same thing as above. We're going to try to follow the same steps here. So first, let's go ahead and try to find all our critical points. So to do so, we look at our derivatives. Our x derivative here will give us a y minus 2x minus 2. And we need to find when this is equal to 0. We also have to take the y derivative, and this will give us an x minus 2y minus 2. And we also need this to be equal to 0. So this is the first time we've had a look at this, but now we've got a system of equations, right? I've got 2 equations here and 2 unknowns. So I might have to solve for one and plug it into the other. So what I'm going to do is take the first expression. Not mean to be a straight line. So from the first expression here, I know that y is equal to 2x plus 2. And I'm going to go ahead and I'm going to plug it into our second expression here. So that we have x minus 2, 2x plus 2 minus 2. And this is still equal to 0. So this will give me a minus 3x minus 6 is equal to 0, or that x is equal to negative 2. Okay, now that I know x is equal to negative 2, I can go ahead and plug this back in to my relationship here, which tells me that y is equal to 2 times negative 2 plus 2 is equal to negative 2. So one critical point, or I should say we have only one. So you might see examples where you have more than one critical point, and in that case, you would definitely have to test each one. But lucky for us, we only have one critical point here. So now, sorry, we have to do our second derivative test. Let's go ahead and calculate out all those derivatives. So fxx is -2. We have that fyy is -2. And then we have that fxy is equal to 1. So when we look at our second derivative test at -2, -2, lucky for us, these are all still constants. This is -2 times -2 minus 1 squared. This is equal to 3. Okay, so that means D is positive. So D being positive means that we either have a max or a min. So we have to look at the sign of either our fxx or fyy. And since they're negative, so we can say either fxx or fyy is negative, and D is positive, we know that -2, -2 is a local max. We can even say with a value of f at the point -2, -2, we plug that in and gives us 8. Okay, we have about 10 minutes left, and I don't want to talk about the next topic until we have a little bit more time left. It's going to be talking about when we introduce boundaries to the regions that we're considering. So all of the examples that we've done today have been just the infinite function in any direction, right? Can we find any local min or maxes on this surface? But now we're going to be restricting ourselves to finite domains, and we'll have to talk about what it means along the boundaries, because we can have local mins and maxes in the interior as well as on the boundary itself that we have to consider. Okay, so I'm going to stick around for another 10 minutes to answer questions or anything like that. Otherwise, take care, stay safe, and I'll see you tomorrow.